Let's go back and remind ourselves of a rule for differentiation that we covered a while ago. D by dx of the ln of x. What do I get when I differentiate the natural log? 1 over x. Good, so 1 over x. So if I were to then integrate this, both sides with respect to x, let's keep in mind what the integral does. The integral is the opposite of the derivative. So on the left-hand side, these two things would cancel each other out. I'll get ln of x equals the integral of 1 over x dx. Of course, there'd be a constant here as well. But in general, the rule to keep in mind is that when you integrate something of this form, and we'll write it in general, the integral of 1 over u du equals ln of u. And technically there's an absolute value around that, ln of the absolute value of u. Yay! So this is what we're going to work with in this section. We're going to need to put things into this form in order to integrate these things. One of the tricks you're going to learn along the way is a reminder about synthetic division. So let's start with problem number 4 to start with. So the integral of 1 over x minus 5 dx. Now this one's not quite in that basic form, so we can make a quick little U substitution to put it in that basic form. I could let u equal x minus 5. Du by dx would be 1. Or in other words, du equals dx. Now this is really nice. If du equals dx, basically you can kind of do these things in your head. And if you're comfortable doing that, that's okay with me. There are certain ones that you can do in your head. Let's follow through with the U substitution though. I get 1 over u du, which is going to integrate to the ln of the absolute value of u plus a constant, or better yet, the ln of the absolute value of x minus 5 plus c. Okay, nice. Like I said, some of you could probably do this. In Calc 2, when you start creating Taylor series polynomials and things like that, you might want to just work on integrating some of these things in your head, just doing a quick mental check that, oh yeah, du equals dx, and integrating it directly. But what about something a little bit more involved, like problem number 8? The integral of x squared over 5 minus x cubed dx. What should catch your eye is that in the denominator you've got a cubic polynomial, in the numerator you've got a squared polynomial. Something squared is a derivative of something cubed, so the natural tendency then is to set this is equal to u and see if we can't make this your du. Now let u equal the whole thing, not just the minus x cubed or the x cubed, but the 5 minus x cubed. The nice benefit here is that when you differentiate, you're going to get rid of that constant. You'll end up with minus 3x squared dx. Now that's pretty close to what I have in my integrand. I've got an x squared dx. Let's get rid of the minus 3. Can't exactly make it vanish, but you can move it to the other side. So let's rewrite this then. That's going to be negative 1/3 du over u. If it helps you, you can take that negative 1/3 out in front. What do I get when I integrate? That's a du. Let's make that look a little bit more like a du. What do I get when I integrate du over u? Yeah. So negative 1/3 ln of the absolute value of u plus a constant. Make sure that when you're all done with this, you go back and substitute for u. U is 5 minus x cubed. And that's it. Nice. All done with that one. Let's try a couple more on the friendlier side. And maybe one or two that aren't on the exactly friendly side. In fact, let's work with synthetic division next. So we'll do 2 in a row to help give you a chance to catch on to synthetic division. So start with problem number 16. 2x squared plus 7x minus 3 divided by x minus 2 dx. Now this one is not exactly ripe for a U substitution because the denominator, is a linear polynomial. That would be the derivative of the numerator, but we need to do things kind of the other way. All right? I'm not going to get my du term in the denominator very often. So what I'll do first, because the numerator is bigger in degree than the denominator, is I'll do a little division. X minus 2 into 2x squared plus 7x minus 3. If I do it this way, it's long division, which is really, like its name implies, long. So let's do it synthetically. Synthetic division says you're just going to work with the coefficients. So the coefficients here are 2, 7, and negative 3. Out front, whatever this term is, you're going to change the sign. So if it was x plus 2, I'd have a minus 2. Since it's x minus 2, I've got an x plus 2. So change the sign. Now let's think about something for a second. If you divide an x squared term by a term of x, the power of the quotient should decrease by 1, right? You start out with a squared polynomial, you're going to end up with a linear polynomial of the first degree. Same thing should happen here. Put a little bar here between these last two numbers. This term here is going to be your remainder. There's 2 steps in this process. You're going to add to go down and multiply to go up. Now in this first case, there's nothing to add. So 2 plus 0 is 2. Multiply to go back up. 2 times 2 is 4. Add to go down. You get 11. 2 times 11 is 22. Add to go down is 19. How did this help me? Well, it does actually help a lot. What this is your constant term. This is your coefficient of x. If I add any other terms here, it would be the coefficient of x squared, x cubed, etc. It's going to increase from right to left. I can rewrite my integrand now as 2x plus 11 plus 19 over x minus 2. These first two terms are things we can integrate. What's the integral of 2x? X squared. X squared plus 11x plus the integral of 19 over x minus 2 dx. And maybe you can do this one in your heads, maybe not. You can factor out the 19. You can do a U substitution. 19 times the integral of du over u where u equals x minus 2, du equals dx. One thing that I see from time to time is people leaving a mixture of u's and x's. Final answer should all be in terms of the original variable. So please make sure you go back and substitute that in. 19 ln of x minus 2 plus a constant. The trick here that really helped us out, though, was the synthetic division. So you're going to add to go down and multiply to go up. So add straight down. First one always starts out with a 0. Multiply to go up. Multiply to go up. Add to go down. Last one there is your remainder. So quickly review there of synthetic division. And I'll give you a chance to work on this yourself in the form of problem number 18 in just a second. Before I move to problem number 18, how are we looking on 16? All right, you're up for problem number 18. The integral of x cubed minus 6x minus 30 over x plus 5 dx. Same kind of thing here that we had with the previous one. And that is the degree in the numerator is bigger than the degree in the denominator. So we're going to get rid of that situation by a little synthetic division. Two things we have to be careful about. The first one, let's take care of this together. What number am I going to put out in front here? -5. The second one, I need to list all the coefficients here. And there's actually a coefficient missing. It starts out with a 1. What's the next coefficient? 0. Because there's no term for the x squared. So it's missing. You have to account for it in the synthetic division. Then a -6, and finally -30. So there's kind of a little nudge in the right direction. See if you can't finish this off by synthetic division. That. All right. Even if it's 20 in the book, let's just leave it as -30. I'm sure this is what the author meant. It's funny how I know what the author meant more often than he does. Okay, so let's take a look at the synthetic division. This always starts out with a 0, a 1 here, -5, add, going down, gives me a -5 again, multiply gives me 25, -5 times -5, add, multiply, -95, add, -125. Woohoo. So keep in mind, this is always your constant. Then the power of x, x squared, x cubed, etc. We don't need to go that far. This is your remainder. In the month of December, it becomes your reindeer. That's all right. All right, cheap humor there. X squared minus 5x plus 19 minus 125 over x plus 5. All of that dx. Let's just integrate it from here. This is going to be x cubed over 3 minus 5 over 2 x squared plus 19x minus 125. Now, if you do that U substitution, du is going to equal dx. You can pretty much tell that that's going to be the natural log of the absolute value of x plus 5. Let's not forget the all-important constant of integration. How many of you got that one? Yeah. Question here? What that would mean is that this is a lower bound for the roots of this polynomial. So the roots of this polynomial are bigger than -5. Yeah, so I'm impressed that you remember that. That's good. I mean, even my algebra students don't learn that. I don't even teach that anymore because the graphing calculator has made so much of a difference in the way you approach these things. So that's impressive that somebody taught it to you at some point. Anything else on problem number 18 here? All right. You guys have worked really hard so far in this section, so we're going to relax for a moment and build a houseboat. Ready to build a houseboat? All right, cool. Let's build a houseboat. So the way we build a houseboat is this. We're going to integrate this. 1 over cabin d cabin. Now, you can do it by a U substitution or not. It's up to you. But if you do this, if you integrate it, what are you going to get? Well, you're going to get the log of cabin, right? But that's not all. You get the log cabin, but what else? Plus a constant. So you've got a log cabin plus the c. Log cabin on the c. There's your houseboat. Yay! Oh, come on. I waited all semester for this one. Give me a little love on this one. Yay. All right. I was so excited today. I'm like, oh, yeah, I can do the log cabin joke. All right. Let's do a couple more here. Round out the section. And basically, these are, more and more U substitutions. Sometimes they're a little trickier than others. And it's also going to be some practice with changing your limits of integration. Let's try problem number 24. So the integral of 1 over x to the 2/3 times 1 plus x to the 1/3 dx. Now this is where your practice pays off. Because if you're just doing a couple of these to get through the homework and you don't practice a problem like this, you're not going to get it. What's your first tendency to want to do in a problem like this? U substitution? If you use substitution, then you're above the average because most people are going to want to distribute. It's like, oh, hey, look. If I distribute there, then I get x to the first power. Wow, cool. But a U substitution is the correct way to go. What would you let U equal, though? Ooh, let's take a look at that. If we let U equal 1 plus x to the 1/3, then du would be, well, let's do du by dx, would be 1/3 x to the -2/3. Right? And that's pretty close. Let's look at this another way. That means du is going to equal 1/3 times 1 over x to the 2/3 dx. And a lot of that we have in our integrand. In fact, let's rearrange our integrand. I'm going to write it as 1 over 1 plus x to the 1/3 times 1 over x to the 2/3 dx. So just a little rearrangement of that problem. That looks like this right here. They match. So what's the last thing that I have to do to kind of whip this problem into shape as far as my du term is concerned? Multiply by 3. So instead of dividing, I'm going to end up multiplying, but I'll get a 3 du equals 1 over x to the 2/3 dx. Now I can make a direct U substitution. But the difference about this one is that our du term actually ended up in the denominator. It's a little bit unusual for our du substitutions, but there's nothing wrong with it. 1 over u times 3 du. Can anyone integrate this without factoring out the 3? Just tell me what I get when I integrate it. What's the 3 ln of u, or 3 ln of 1 plus x to the 1/3. Not so bad. I'm not sure that any of you have really taken the time to memorize this one, but you don't necessarily need to any longer. And that is the integral of the tangent. There is a way to integrate the tangent. There's a formula for it. But suppose you don't remember that. Then another way you can come at this is to rewrite the tangent in terms of trigonometric functions, of sine over cosine. Sine of 5 theta over cosine of 5 theta. Does that help at all? What could I do now? U substitution, right? Now, you don't want to let u equal sine of 5 theta because you're not going to be able to find your du term in the denominator. When you differentiate this, your du term is going to be up in the numerator still, so that won't work. If you let u equal cosine of 5 theta, then du by d theta would be what? Good. Minus sine of 5 theta times 5. Good. Times 5. Because you have to use the chain rule here. Du is minus 5 sine theta, 5 sine 5 theta, d theta, and then kick that constant to the other side by dividing both sides by negative 5. And that's perfect because sine of 5 theta d theta is exactly what we have right there. Okay. Let's finish up our integration. I get negative 1/5 du over u, which we can integrate pretty easily. The negative 1/5 natural log of u plus a constant. Ln of, let's see, where was it? Cosine of 5 theta plus a constant. Now, if you're thinking back, if some of you happen to actually remember the formula for the integral of the tangent, you might recall there's a secant involved. Oh, well, wait a minute. We got a cosine and there was a secant here. You can turn this into a secant. Let me do it this way. I'm going to take the negative here and use it as an exponent for this expression. So cosine of 5 theta to the negative first power. So I'm just using the power rule for logs. But something to the negative first power is a reciprocal. So 1/5 ln of 1 over cosine of 5 theta in absolute value. And what's 1 over the cosine? It's the secant. Ln of the secant of 5 theta. So I got rid of the negative there and turned this into a secant. It's not a big deal. It's not something I expect on an exam. Just showing it to you in case you're curious about, well, wait a minute, I expected a secant. You're essentially getting the same answer. So let's do 2 or 3 more. Well, maybe 4 more. Ah, I know. So brutal. So brutal. We'll start with problem number 46. Let's try it again. dy by dx equals secant squared of x over tangent of x plus 1. It says something about passing through the point pi and 4. Okay. Well, what they want you to do is they want you to solve for y. So one thing I can do is multiply both sides by dx. And then I'll get the dx's to cancel on the left-hand side. dy equals secant squared of x over tangent of x plus 1 dx. I don't know. I'm not sure. Did I get any closer to solving for y? Maybe a little bit. What else do I need to do here to solve for y? Good. Integrate both sides. So let's do that. On the left-hand side, you get a y. Technically, you get a y plus a constant, but let's just leave the constant to the right-hand side. What am I going to do to integrate the right-hand side? Yeah, u equal the denominator, right? Because what's the derivative of the tangent? Secant squared. The derivative of 1 is 0, so we'll let u equal secant squared. No, how about u equals tangent of x plus 1. I'm getting ahead of myself. Du is secant squared of x dx. So that's perfect. This lines up. This becomes the integral of du over u. Substituting in for u, get the natural log of the tangent of x plus 1 plus a constant. Okay, let's figure out what that constant is. You're given that the function that we want to find passes through this point, pi and 4. There's a whole lot of choices that we can use for C, but only one of them is going to make it pass through this point. Would it be helpful to see a graph of this, or are we good? Good? Okay. Let's plug in pi for x, and we should get 4 for y. So 4 should equal the ln of the tangent of pi plus 1 plus a constant. Let's do some thinking here. What's the tangent of pi? 0. And that gives me the log of 1 then. So if that's 0, then it tells me that c is 4. Therefore, c equals 4. Be careful how you say C4. The Department of Homeland Security will be down on you like that. All right. Tangent of x plus 1 plus 4. All right. Not so bad. So another nice one with a U substitution resulting in a natural log for the integral. We're going to do a couple to practice changing our limits of integration. Those next two would be problems. We'll start with problem 54. The integral from e to e squared of 1 over x ln of x dx. Now this one's a little challenging. It's not at all obvious what to choose for any U substitution. ln x? Well, maybe I'm wrong. Maybe it is obvious. Nailed that one pretty quick. So let's try it. If u equals ln of x, Hamza, what's du going to equal? 1 over x dx. And we can kind of separate that out a little bit. E to the e squared of 1 over ln of x times 1 over x dx. So just splitting that up. And this is perfectly my du term. The difference is here that this is a definite integral. Personally, I'd just change your limits and be done with all your substitution work. How do you change your limits? Well, we're going to evaluate this function at these endpoints. So I want the u equals the ln of e, and so let's call that u of e, and then u of e squared. Ln of e squared. What's the natural log of e? 1. Now for the natural log of e squared, you can bring the 2 out in front and get 2 times the ln of e. So the ln of e squared would be 2. The nice thing about changing our limits is that we're not going to have to look back at all. You're going to get the integral from 1 to 2 of 1 over u du. So it's a natural log of u. Do I need a constant plus c? Not really, because if you put in the plus constant, it would subtract itself off because you've got a definite integral. So we don't need the plus c here. I don't need the absolute value either because these terms are already positive, so it's the ln of 2 minus the ln of 1. What's the ln of 1? 0. So overall, you get the ln of 2. Make sure you practice some with definite integrals because you're going to need to do substitutions and change limits. Or the other way that you could have done it would be to write, say, a and b here, and then substitute in ln of x and finish it up that way. At that point, when you make your substitution back in for x, then you can put in the limits of 1 or e and e squared again. Your turn for 1. Problem number 72, unless you have some specific questions about problem 54. The integral from pi over 4 to 3 pi over 4 of, I think it's 72. Which one is it? Oh. Let's just put a question mark here. Integrate this one. Sine of x over 1 plus cosine of x dx. Making me look bad. Basically, it's asking you to find this area. So it's a nice reminder of the correspondence between our integrals and this area. So it's the area underneath this curve between pi over 4 and 3 pi over 4 and above the x-axis. Hopefully what suggests itself is a U substitution. U could equal 1 plus cosine of x. Du equals minus sine of x dx, which we pretty much have except for the negative sign, so I'll divide both sides by -1 dx. And then let's do something else. Let's change our limits of integration. Let's just get rid of the x's altogether. So u at pi over 4 is going to be 1 plus cosine of pi over 4. Cosine of pi over 4 is square root of 2 over 2. At 3 pi over 4, cosine of 3 pi over 4 is just minus root 2 over 2. So let's integrate this now with our new limits. That's going to be the integral from 1 plus root 2 over 2 to 1 minus root 2 over 2 of minus du over u. So the minus can come out in front. That's minus the natural log of the absolute value of u between these limits. If you're bothered by this negative, you could make this a positive if you switch these limits. Same thing here. I'm not going to worry about that. Let's just leave the negative out in front. That's going to be the natural log of 1 minus root 2 over 2 minus ln of 1 plus root 2 over 2. If I distribute this negative sign, I get minus ln of 1 minus root 2 over 2 plus ln of 1 plus root 2 over 2. Since I'm subtracting these things, I can use the quotient rule to bring them together. Quotient rule for logs will give me 1 plus root 2 over 2 over 1 minus root 2 over 2. This isn't bad. I'm not going to complain if you leave an answer like this. I'm just going to go a little bit farther, because if you did a problem like this in the book and you looked up your answer, you're going to see something that looks a lot different than yours. The book's going to get rid of this complex fraction. They would multiply everything by 2 over 2 and get the ln of 2 plus root 2 over 2 minus root 2. I think that's a good enough place to leave it. You could probably actually go a little bit further there if you wanted to. But that's good enough to leave it here. Let's check that out in a couple ways. Before I do that, are we okay with this much right here? All right, let's check that out on our calculators. So it would be the ln of, let's see, you hit the alpha key, then the y equals key. Let's do a nice fraction, especially in this kind of an expression. It's going to help out. 2 plus the square root of 2 over 2 minus the square root of 2. And then a right parenthesis there. Okay. And let's compare that to the area. So the function here, one way to do this other than the numerical integration, let's see, let's do alpha y equals, then sine of x over 1 plus cosine of x. Let's set our window from 0 to pi. Tick marks every pi over 4 units. Zoom fit. So what I want to do is I want to compare the numerical expression there with what I get from integrating on my calculator. All right, any day. There we go. let's integrate. So we'll integrate from pi over 4. So second pi divided by 4. That's the lower limit. Oh, that's all right. Yeah, you're right. I clicked differentiate. Sorry. 7. Integrate. Pi over 4. That's the lower integral. And the upper one is 3 pi over 4. Ooh, ah. You know, I'm getting a different value here. Yeah, something's wrong. Where could we have gone wrong? Let's try back up here. See if we maybe made a mistake in rationalizing our expression somewhere. I don't see a mistake. Let's see. There. Let's just compare that to minus ln of 1 minus root 2 over 2 is same thing as 2 to the negative 0.5 power. Plus ln of 1 plus 2 to the negative 0.5 power. I'm getting something different there, aren't I? Did you get 1.7? So you're getting the same thing we got when we did this numerically. Graph y equals. Yeah, I'm not understanding why they don't match. Beautiful. Thank you. That's exactly right. Mode, radians. God, hate when that happens. All right. So let's do it this way. Let's just do a brute force approach. There we go. Now they're the same. Thank you, Ashley. Well done. Okay, I'll tell you what. I appreciate that. Let's get out of here really quick with this last problem, number 66. Kind of a refresher, reminder. The integral from 0 to x of the tangent of t dt, we'll call that f of x. Find f prime of x. All right, I'm going to walk around, and if you guys got this, we can go. For homework, don't shout out any answers, please. 1 through 23, 27, maybe 29, I don't know. 35 through 45, 51 through 57, 65 through 73. But those are just the odds, though, okay? And I'll give you a week to do it, all right? A whole week. You've got a week. All right, let's see how we're doing on this one. See the right answer, you can go. section 5.4. Alright, so for the rest of you, still going, wait, I don't get it. From the so-called second fundamental theorem of calculus, what does f prime of x equal? Tangent of x. Just drop that into the integrand, tangent of x. The second fundamental theorem, section 5.4, you might want to look at it. Have a great, healthy, happy Thanksgiving. Go Lions, but more importantly, go blue. See ya.